Hello everyone, welcome to my presentation. My name is Xiuheng Wang. It's my great honor to participate in ICASSP 2023. Now let me introduce our recent work on change point detection with the neural online density ratio estimator. The aim of the change point detection is to detect abrupt changes in the different state of the time series measurement. As a very fundamental problem in the field of statistics and signal processing, it had a very wide range of applications. In medical monitoring, it can be used to detect changes in EEG signals to monitor some brain diseases. In speech recognition, it helps segment some audio signals, although it's a very useful tool in video analysis. Now let's formulate the change point detection problem. Assume there is a time index TR where there is a change in the statistical distribution of XT. Before TR and after TR, XT is in two different distributions. We say TR is a change point. The change point detection problem consists of estimated TR with following requirement: high detection rate, low false alarm rate, and low detection delay. Current change point detection approaches can be roughly divided in two categories: parametric and non-parametric. The parametric ones rely on model assumption of explicit form and PX and QX. Examples include cumulative sum, generalized likely ratio test, and subspace identification. However, there are some limitations of parametric approaches. First, it's normally complicated to derive an accurate model to describe PX and QX. Second, the related parametric approaches are usually sensitive to modeling error. In contrast, non-parametric approaches avoid such assumptions. This technical route is developed with particular interest in density ratio estimation. That is, evaluate the density ratio of Px, X, and Qx as given in equation 5. The motivation is that if we know Px and Qx, we can easily calculate Rx, but not verse-wise. It means if we want to know Rx, it's unnecessary to know Px and Qx, so that Rx is easier to estimate. Exemplary approaches are based on impedance estimation using KL divergence and the unconstrained least square. All the methods discussed above are offline. Recent online algorithms process streaming data in an adaptive fashion. For example, an online method, lookup, minimizes a special designed objective function with color machine to learn the following density ratio with data in two sliding windows. In this work, we further advance this line of research to estimate the density ratio at each time instant. To this end, we consider three steps. First, we formulate the density ratio estimation as a binary classification problem. Second, we consider powerful neural networks to estimate the density ratio. Finally, we use continual learning strategy to achieve online detection. Now I give more details. In the first step, we label the samples in two windows with 0 and 1, and express related probabilities as conditional probability. Using Bayes' rule and assume that the marginal probability of two classes are equal, the density ratio can be written in the form of the equation 6. In this way, the density ratio can be regarded by optimal binary classifier. Second, we parameterize the classifier as sigma f phi x, where sigma is a sigmoid function and f phi is a neural network. When the classifier is well trained, the optimal value for network parameters yields our neural online density ratio estimator, as given in equation 7. Then we detect the changes point by summarizing the test statistic in test window and compare it to given threshold. Combining two datasets as a training set dt, we aim to learn a binary classifier based on dt at each time instant. It's beneficial to retain knowledge acquired from dt-1. To this end, we investigate a variational continual learning strategy with this learning objective. It contains minimizing the KL divergence of neural networks between two time instants. Now we turn to validate our approaches. The network architecture is given in this figure. It contains three hidden layers. We consider these three online and non-parametric baseline to compare. The length of the reference and test window are both set 64. First, we consider generating simulated data for Monte Carlo experiment. The simulated data is generated from a Gaussian mixture model. We generated 700 samples and put a change point at 400. This figure illustrates the mean and standard deviation of test statistic for all compared methods. The yellow line is the change point, and the red line is the change point plus window length. We observe that node achieved the best performance. This can be seen more clearly in the ROC curves in this figure. The closer a ROC curve is to the upper left corner, it involves less false alarms and higher detection rate. Now we further evaluate our method node with two instances. One is critical detection. The real data is composed of transactions and processed with PCA, and the first 5 components were used. We created 2 change point detection by inserting the fraud in the genuine transactions. The results are given here. We can see that our method has the best performance with less false alarm when there is no change point. Another instance is text language detection. The real data contains 17 different languages. We clean and represent it using linear embedding model with dimensionality 20. We created 2 change points by contacting 3 languages. From this test statistic in this figure, we can see that MA, Nougat, and Node provided comparable results. However, Node test statistics are more stable outside the change point. That's all my presentation. Thanks for your attention.